Hello, this is Group 3, which includes Devin, Garrett, Jarell, Sebastian, and Taha, and also me, Kashyap. And this is our STA3023 Team Project 2. Now the situation is the following. We are quality control engineers at the Ford Motor Company. However, an unknown number of gears being produced at the factory have defects, and accordingly, we must find the actual population proportion of defects so that the engineers can decide whether to continue the production or withdraw it to improve it. Now there are two statistical methods and solutions founded on inferential statistics that we can use to solve the problem, and they're also used by engineers to solve problems like quality control and system optimization, and are great for hypothesizing sample data to proportion data, which we will be doing in this case. The first is point estimation, which is a simple calculation, but fails to consider inevitable variability within samples. The second is confidence intervals, which may be more precise, but doesn't give an exact proportion and is sensitive to the sample size. First off, on point estimation, we can utilize the mean point estimation of a randomly selected batch to determine a rough estimate on how many of these helical gears have defects. The calculation is fairly simple, with the population estimate P over population being equal to the number of defects X divided by the total population N of helical gears. However, it also has its drawbacks, as the point estimate is not an exact representative of the entire population, and is instead just based on a small randomly selected sample. And the second is that variability will indeed be present, and this formula does not account for it. That's why we'll be using the second confidence interval also, to determine what proportion of helical gears have defects in the factory. The confidence intervals we calculated using the formula pictured below, where A is equal to 1 minus confidence level, P is the sample proportion of defects, Q is 1 minus P, N is equal to the size of the sample, Z is the correct value, and we're doing this all at a 95% confidence level. The formulas are given below with a lower and upper limit, but it also has its drawbacks, as we will only know a range of possible proportions that will continue the true proportion at a certain confidence and not the exact estimate. Secondly, this calculation is slightly more arduous than the last one given by the formulas, and is also influenced heavily by sample size. Now that we know our methods, let's calculate and do a statistical analysis so that the Ford Motor Company can come to a conclusion. Now in this case, we're just going to be using a code to simulate a hypothetical situation using a C code script that I compiled. And the code presents the following data given that the hypothetical historical defect rate for the product has been 10% and the sample is 100. And the code presents that the number of defective products in a single trial is 16. Now we're going to do the calculations, and the point estimate arrives at the point of estimation of the defect rate is 0.16 or 16%. The confidence interval noted at a 95% confidence level, which has a Z score of 1.96, has a lower bound of 0.1 and an upper bound of 0.244. Now let's do our statistical analysis, and accordingly the calculations arrive at the following data, and that the point estimation is 1.16, and that the confidence interval for defect rate with a 90% confidence level is approximately 0.101 to 2.44. Subsequently, given the possibility of defect rate is rising to as high as 25% compared to its historical level of 10%, it would likely be wise for administrators to strengthen quality control for their helical gears. And it would be prudent to involve more rigorous inspections, improve manufacturing processes, or enhance testing procedures to reduce the defect rate. In conclusion, utilizing proportion confidence intervals provides insight into the true proportion with the confidence level. It enables determination of defective helical gear proportions using point estimates. In addressing the problem, statistical findings facilitate communication with factory assembly line, and it allows for minor adjustments for improvement and better quality control on the assembly line. Overall, confidence intervals and point estimations aid effective issue resolution, ensuring high-quality helical gears being produced at the Ford Motor Company. These are our references, the first one being the textbook, the second one being the picture, and the third one being a code that I compiled.